Now we are going to look into the most important component of cluster architecture. Kubernetes cluster is controller. So the controller in robotics and automation, a control loop is a non-terminated loop that regulates the state of a system. Yes or no? If anybody has come from mechanical background or ECE or that's telecommunication background or triple background, you might have heard about this, or operations and process automation, you might have heard about that automation. So basically automation is a control loop, is a non-terminating loop that regulates the state of a system. So now you may think, what is the difference between that control loop and this controller? I'm going to tell you, don't worry. So here is one example of a control loop. Example, let's take a thermostat in a room. Okay. When you set the temperature, that's telling that thermostat about your desired state. When you set a temperature, a certain temperature, example, a 23 degrees Celsius in your thermostat, that means you are telling the thermostat about your desired state. That's what I want. That's what the temperature I would like to have in this room. Okay. The actual room temperature is the current state, but at that moment the actual room temperature could be 32 degrees Celsius. That 32 degrees Celsius is the current state. So the thermostat acts to bring the current state, which is 32 degrees Celsius, closer to the desired state, which is 23 degrees Celsius, by turning the equipment on or off. Here, what is that equipment? It is not that important for us because we are neither dealing with AC nor dealing with refrigeration. Okay, but the thing should be understood is the difference between a current state and a desired state. So similarly, in Kubernetes, controller controllers are control loops that watch the state of your cluster, then make or request changes where needed. Each controller tries to move the current cluster state closer to the desired state. That's what the purpose of controller. A controller tracks at least one Kubernetes resource type. So these objects have a spec field that represents the desired state. The controllers for that resource are responsible for making the current state come closer to the desired state. Current state come closer to the desired state. So unlike manually created pods, the pods maintained by a replication controller are automatically replaced if they fail. So that is one more. The most important benefit of controller is, if you take it, there is another type of controller that's called a replication controller. A replication controller are automatically replace a pod if it fails, if it gets deleted, if it gets terminated, whatever it may be, that is going to be replaced. So there are several controller types such as a replication controller, deployment controller, all those things we are going to look into it now. So control via API server. The job controller is an example of Kubernetes built-in controller. This is a built-in controller and a widely useful controller. Built-in controllers manage the state by interacting with the cluster API server. So job is a Kubernetes resource that runs a pod. This is also an important aspect. Job is a Kubernetes resource that runs a pod or perhaps several pods to carry out a task and then stop. So once scheduled, Pod objects become part of the desired state for a kubelet. When the job controller sees a new task, it makes sure that somewhere in your cluster, the kubelets on a set of nodes are running the right number of pods to get the work done. The job controller does not run any pods or containers itself. Instead, the job controller tells the API server to create or remove pods. Other components in the control plane acts on the new information, and eventually the work is done. After you create a new job, the desired state is for the job to be completed. The job controller makes the current state for the job be nearer to your desired state, creating pods that do the work you wanted for the job, so that the job is closer to completion. Controller Controllers also update the objects that configure them. For example, once the work is done for a job, the job controller updates that job object to mark it finished. It seems like how thermostats turns a light off to indicate that your room is now at the temperature you set. So always, if you are a mechanical engineer or automobile engineer, just compare a thermostat with your controller of Kubernetes. It would be much easier. To the analogy will give you a complete understanding. So now there are different types of control, out of which the first one is a direct control. Direct control, in contrast with job, some controllers need to make changes to things outside of your cluster. For example, if you use a control loop to make sure that there are enough nodes in your cluster, then that controller needs something outside the current cluster to set up new nodes when needed. So controllers that interact with external state find their desired state from the API server, then communicate directly with an external system to bring the current state closer in line. The important point here is that the controller makes some changes to bring about your desired state and then reports the current state back to your cluster's API server. Other control loops can observe that reported data and take their own actions. In the thermostat example, again we are taking the analogy. If the room is very cold, then a different controller might also turn on a frost protection heater. With Kubernetes cluster, the control plane directly works with IP address management tools, storage services, cloud providers, APIs, and other services by extending Kubernetes to implement the similar kind of feature or function. So now let's see the difference between the desired state versus current state. So the Kubernetes takes a cloud native views of systems and is able to handle constant change. Your cluster could be changing any point as work happens, and control loops automatically fix failures. This means that potentially your cluster never reaches a stable state as long as the controllers for your cluster are running and able to make useful changes. It doesn't matter if the overall state is stable or not. And let's see some of the ways of running controllers. Kubernetes comes with a set of built-in controllers that run inside the kube controller manager. These built-in controller provide important core behaviors. First one is the deployment of controller and job controller are examples of controllers that come as a part of the Kubernetes itself. They are built-in controllers. Deployment controller and job controller. These are two built-in controllers. Kubernetes lets you Kubernetes lets you run a resilient control plane so that if any of the built-in controllers were to fail, another part of the control plane will take over the work. So you can Find controllers that run outside the control plane to extend Kubernetes, or if you want, you can write a new controller yourself. You can run your own controller as a set of pods or externally to Kubernetes. What fits best will depend on what that particular controller does. So then we have a controller types. We will look into various controller types here. The first one is a replication controller. Of course, there are a lot of controllers, but mainly we will be looking at the most important controller and which are widely used in Kubernetes. A replication controller A replication controller is responsible for running the specified number of pod copies, or in a proper Kubernetes language, we can say that replicas across the cluster. The main function of replication controller is to maintain the replicas that you have desired. That is our desired state. If the current state has been changed to, see, for example, our desired state is 5, but because of some unhealthy issue during the checkups, if the pod has been turned off, if the pod has been removed, then automatically the current state will become 3. Then the replication controller comes into the action and it will make the current state as a desired state. It will start a new 2 or sorry, it will start 2 more pods, and then it will make a desired current state as a desired state. Then we have one more controller, that is a deployment controller. A deployment defines a desired state for logical group of pods and replica sets. It creates a new sources or replaces the existing resources if necessary. A deployment can be updated, rolled out, and rolled back. A practical use case for a deployment is to bring up a replica set and pods. Then update the deployment to recreate the pods. For example, to use a new image, later deployment can be rolled back to an earlier version of the current deployment if current deployment is not stable. Then we have the final type that we are going to talk here is the replica set. So a replica set is that next generation replication controller. A replication controller supports only equity based selectors, while a replica set supports set based selectors. Now let's look into the cloud controller manager. So cloud infrastructure technologies let you run Kubernetes on public, private, and hybrid clouds. Kubernetes believes in automated API-driven infrastructure without tight coupling between components. The Cloud Controller Manager is a Kubernetes control plane component that embeds cloud-specific control logic. The Cloud Controller Manager lets you link your cluster into your cloud provider's API and separates out the components that interact with the cloud platform from components that only interact with your cluster. By decoupling the interoperability logic between Kubernetes and underlying cloud infrastructure, the Cloud Controller Manager components enables cloud providers to release features at a different pace compared to the main Kubernetes project. The Cloud Controller Manager is structured using a plugin mechanism that allows different cloud providers to integrate their platforms with Kubernetes. And anyway, we are going to integrate AWS cloud platform of my account with Kubernetes, and we are going to work on one Kubernetes project. So Cloud Controller Manager functions. The controllers inside the cloud controller manager include a node controller, a route controller, and service controller. A node controller is responsible for updating node objects when new servers are created in your cloud infrastructure. The node controller obtains information about the hosts running inside your tenancy with the cloud provider. The node controller performs the following functions. One, it updates a node object with the corresponding server's unique identifier obtained from the cloud provider API. One, and second, annotating and labeling the node object with the cloud specific information such as the region the node is deployed into and the resources that has available. And three, obtain the node's host name and network addresses. And four, verifying the node's health. In case a node becomes unresponsive, this controller checks with your cloud provider's API to see if the server has been deactivated or deleted or terminated. If the node has been deleted from the cloud, the controller deletes the node object from your Kubernetes cluster. Then let's look into the route controller. Route controller is responsible for configuring routes in cloud appropriately so that the containers on different nodes in your Kubernetes cluster can communicate with each other. Depending on the cloud provider, the route controller might also allocate blocks of IP addresses for the pod network. Then the last one is our service controller. Service controller integrate these services integrate with cloud infrastructure components such as managed load balancers, IP addresses, network packet filtering, and target health checking. The service controller interacts with your cloud provider's APIs to set up load balancers and other infrastructure components when you declare a service resource that requires them. And finally, authorization. This authorization section breaks down the access that the cloud controller manager requires on various API objects in order to perform its operations.